Yeah, so I will be presenting a generic and mechanizable framework called TrackDev and showing its application to real protocols and its mechanization in therein. Perfect. So first off, what is trackability? To answer that, we look at the notions of security versus privacy, and security is the more known term in the sphere of computer science. So it represents the protection against information disclosure, so the theft of electronic data, and potentially even the physical protection layer of hardware. Oops, forgot to press the button. There we go. Privacy, however, is the more relevant term for our work. It represents the user's namelessness in a network, and it is the protection of their identity rather than the protection of their data contents. So it's also an umbrella term that covers even more specific notions such as anonymity, unlinkability, and untraceability. But we introduce a new term, trackability. This is not a term that has been used elsewhere in other research as far as we know. So we use it to describe an adversary's ability to link a long-term identifier of a party to some temporary one that is used by the protocol to conceal the party's identity. And this linking allows an adversary to know who sent a certain message. And our flavors of trackability also provide a much finer-grained way to specify privacy than other works. We also introduce a new framework that we call TrackDev, that encompasses several characteristics that make it versatile, so that it's not limited to just one domain, but it is applicable to tracking over any secure application level traffic. And like I mentioned before, it is mechanizable in formal verification tools such as therein. So the framework itself and its characteristics. TrackDev operates on protocols that realize what we call an identification functionality. And in the very first message where we have the client Alice identifying themselves to the server, Bob in this case, we then have some optional messages that Alice and Bob can send to each other, possibly to establish secure communication. We're not concerned with the particulars of these optional steps, but at the end goal of these optional steps and the previous required steps is that Bob knows who Alice is. So the final step is Alice actually accessing the servers that Bob is facilitating. And this message, M3, may not contain the ID of Alice in clear text, may in fact contain a temporary identifier of Alice. So we do not specify what the identifiers are. They can be serial numbers, public keys, virtual identifiers. All we require is that they are uniquely identifying identifiers. We do distinguish between the messages M1, M2, and M3 by referring to messages M1 and M2 as pre-application messages because they happen before the client accesses the application or service, and we call the message M3 the application level message because it happens when they're accessing the application. We also have two functional requirements of the identification functionality, and that is in steps 1 to Q-1, so in the first and the optional steps. B identifies A as part of the message sent, and so regardless if Alice is using a temporary identifier or not, Bob always knows who Alice is explicitly. The second requirement that we have is that in steps Q and thereafter, A is accessing the service that B is facilitating based on the identification that just took place. So we have two types of attackers that we model over Alice and Bob's communication. And the first type is a passive adversary that simply observes the traffic between Alice and Bob and doesn't really do much else. So this is very obviously a weak attacker. And the second type is an active adversary, which is a strong attacker. So an active attacker is able to intercept, block, substitute the messages in the network, and they can also impersonate Alice or Bob, and they have full control over the network. So our strongest attacker is akin to a Dolovyau adversary. This means that the active attacker works on the following aspect of perfect cryptography. So the cryptography of the protocol is perfect and cannot be broken in any way. So the attacker is unable to read the encrypted messages unless they have the necessary key. All our definitions are based on what we call attack setups, and this models a handle to protocol executions which the adversary has access to in order to track the parties in the protocol. And an execution is a single run of a protocol. So every time a user runs a protocol, it is a new execution. So our attack setups S for a given set of executions E contains two sets of messages, so the pre-application messages and the application level messages. The sets that go into the attack setup are arbitrarily chosen, so it may be the case that it is not the entire execution that is used, but only a small part of it. And the adversary then uses this attack setup to track a particular user's application level messages or their actions in the network. So in order for the adversary to track someone, they need to provide a trackability relation TR for the given identifier. So this relation is a pair of the identifier and application messages that belong to the identifier. So the relation is correct and the attacker mounts a successful attack if the messages contain at least some application level messages where the user is accessing the application or service, and then these messages do actually belong to the user that they're trying to track. So what are the characteristics that we have for our framework? We say that the non-trackability is explicit if real long-term identifiers are present in the executions, and the real identifier is used in at least the pre-application or the application level messages or both, and then the protocol makes no effort to hide who the users are. However, we can also say that the non-trackability is implicit if the real long-term identifiers are not present in the executions. So the user communicates using some temporary identifier instead, and we represent these temporary identifiers as a bijection phi of the ID, which just means that the real ID is hidden in some way, but that ID belongs to a given party, in this case, Alice. So we also have static and adaptive trackability. And in static non-trackability, the adversary is not limited to any particular identifier that they need to track. So the ID is not imposed on them by any challenger outside. They are free to choose whoever they want, and thus they remain static in their behavior, which is why I call it static trackability. On the other hand, we also have adaptive non-trackability, where the adversary is required to track a particular identifier. So an outside party now challenges them on tracking someone specific, and they have to now adapt to their behavior, and hence we have adaptive trackability. Finally, we also have session insensitive trackability, where we do not distinguish between the different sessions or executions. The attacker is not required to change their behavior or do anything different than what we've discussed so far. But in session-sensitive non-trackability, the adversary is required to also name which session or execution the messages that they are tracking come from. So this does change our attack setup somewhat, in that now we also index the messages by which session they are from. So far we've covered the active versus passive attacker, explicit versus implicit, static versus adaptive, and session insensitive versus session sensitive. Say that one. We do also have existential and universal types of trackability, but these are a standard where existential is at least one identifier is trackable and universal is where all of the identifiers are trackable. So how do these characteristics compare between each other? So in fact, we actually introduced 32 different notions of non-trackability. However, there are actually even more notions if we leave one or more of the dimensions free, such as simply looking at static non-trackability, which is a valid notion in its own right, so without its flavors of implicit-explicit, active-passive, session-non-session, and universal or existential. So very quickly, as I mentioned here, we use the word non-trackability as a positive notion, so the privacy requirement, whereas when I say trackability, usually it means the trackability attacks or the refutation of the privacy requirement. So our trackability notions add to the world of privacy specifications, as existing notions do not currently consider passive versus active attackers. So additionally, we also separate identifiers to track into both explicit and implicit identifiers, thus creating a much finer granularity for attack specifications. And we provide a clear and generic recipe to formulate the necessary rules and lemmas to demonstrate specifically static explicit trackability in general. We have proven a number of implications between the framework characteristics, such as between passive and active attackers or adaptive and static attacks, when there are also other implications in the paper. But I will quickly go over one now and show that some are even incomparable. So for example, if we have an adaptive trackability attack, we should also have a static trackability attack. However, if we add one more layer of onto them, so if we have the attacker for the adaptive attack be an active attacker, and the attacker for the static attack be a passive attacker, then actually the two are incomparable. So for example, imagine we have a normal able-bodied person and an able-bodied athlete. So if the normal person can get to some distance away, just walking or running something, then we can guarantee that the athlete can as well, because they're obviously much more fit. But if we give the normal person a bicycle and we make the distance longer, we cannot guarantee that the athlete will also be able to reach that destination. So in a sense, the two are incomparable, and that is kind of similar to the adaptive active and the static passive one. So if we look at examples of using our framework, we looked at a protocol called the LoRaWAN Join version 1.1 in this case. So the users in this protocol is represented by the end device, and the server is the collection of the network join and application servers. The pre-application message is the user requesting to join the network with the join request message, and they use a permanent identifier, which is called dev UI, EUI. And then there are some optional exchanges between the servers, and in these steps, a temporary identifier is created called the dev address, which is then used in the application level messages by the device to actually access the network. So this is a static session trackability attack that can be mounted on this protocol with a passive attacker for an explicit identifier. The attack works in the following setting. End devices are already sending application messages and only one new device is joining the network. And we can tell that they're joining the network because they send a very specific message. The attacker needs to produce a trackability relation TR that links the given identifier to the set of messages and the traffic that belong to that identifier. So in this scenario, we have our attacker observing the join request that appears, and Yep, there we go. Observes the join request message that appears in the network, and then they see a soon-to-come join accept message, which comes in a predictable number of seconds as per the LoRaWAN specifications. And they then also see an application level message with the temporary identifier. However, this message is also even further identifiable because it has a frame counter of 0, while all the other devices would have it not at 0 because they've already been communicating on the network. So the attacker now knows the dev address and can thus, use it to track the rest of the messages for this session for that device. So we now look at the application of the framework in practice. And what we've done is we developed on top of a proprietary product called Flora, which is primarily a LoRaWAN traffic sniffer, but it has other capabilities such as decrypting packets or playing packets. And we used it to track these two devices. We had our own two devices send and receive application level packets. And then we randomly disconnected them to force new sessions, so new join requests. There was also other devices owned by us that were present on the network that we were just using as noise to simulate real-life traffic. And we do the attack that I described a couple slides earlier. So for our attack, we target this particular dev UI, which I will not read out because it's quite long. But we see this very first join request for this dev UI, and very closely afterwards we see a join accept. So this does come in a predictable number of seconds, as I mentioned. And then we see an application level message with a frame counter of 0. So now we have the dev address for it, and we can say that these two belong to the same device, and we can use that dev address to track the rest of the messages in that session for that device. However, since we randomly disconnected our devices to force new sessions, we can see the long-term identifier appear again further down in our network traffic, and we can look for the same pattern to get the next session's dev address and thus track the next session's messages. So we have presented all our findings to the LoRa Alliance, and we have actually worked very closely with them. And we're very excited to say that the countermeasures that we presented to them will be present in LoRaWAN Join version 1.2. We have also done our experiments on 5G procedures and the attack. And we have shown that at least one identifier is trackable with a passive adversary or otherwise an existential static trackability attack with an implicit identifier for a passive adversary. And we have done this with two types of network traffic, one which is facing the 5G core and one which is facing between the 5G towers. So how do we mechanize it? We show that encoding in Tamarin either session-sensitive or session-insensitive trackability makes no difference to the mechanization efforts. We show that, in fact, specifically for explicit trackability, it is very simple to mechanize for protocols that have the identification functionality, but it is implicit trackability that requires more effort from the person encoding the lemmas to mechanize, because they would result in a very protocol-specific lemma. So in conclusion, we have defined a new multi-parameter framework called TrackDev to reason about tracking protocol participants in their protocol executions. We show that TrackDev is worthwhile. It has several new privacy notions, over 32 in fact, amendable to both practice and formal verification. TrackDev has yielded novel attacks on the LoRaWAN Join protocol and 5G procedures. We have implemented in a practical toolkit called Flora our privacy attacks on the LoRaWAN Join version 1.1. In fact, our solutions will be adopted in the LoRaWAN Join version 1.2, with whom we're working closely right now. And we have shown that our framework is mechanizable in formal verification tools such as Tamarin. Thank you.
Tamarin Prover has already a notion of observational equivalence to reason about privacy. And I'm wondering how does this notion compares to yours? And I think that the Tamarin also has that notion as sound but incomplete, and how does that relate to your solution?
Yeah, so I have a backup slide, which is the Tamarin lemma that we used for explicit trackability for the LoRa Join. So how we encoded it is why this would work only for explicit and rather than implicit. So we do use observational equivalence. We check that if there are two devices that are joining the network, we only have one that actually completes the successful join for LoRa. We check that they're not the same device, and we check that with the tags that only this one tag at the end of the execution of the LoRa Join appears. So only one actually ends up making it successfully through there. So what we did is we encoded it in such a way so that, I see you're confused. Yeah, so we encoded it in such a way so that if we have only one device joining, because they have the long-term identifier present at the start, we can then link it between the observation equivalence between that device that joined at the end, because we added all our only once tags into the lemma. And then it checks like with the executions with that. But I'm happy to discuss this afterwards in more detail.
Yeah, I feel like.